Good evening, everyone. My name is Mansi Tripathi. I am TA for this course, Wastewater Treatment and Recycling. We are entering the fifth week. One 1 month has been passed, and what we have learned about the quantity and quality of the wastewater generated in our cities. Now, in this fifth week, we'll be talking about the treatment technologies. So basically, there are two types of treatment technologies. What I mean is our treatment technology is categorized in two ways. One is unit processes and other is unit operations. When we talk about unit operations, we talk about all those physical methods that we use to separate the waste from the water. That is for the wastewater treatment. Now, and when we talk about the unit processes, we talk about various chemical as well as biological process that we use for the treatment of our water and wastewater. This week is all about preliminary as well as primary treatment. So these treatments are more or less unit operations, okay, because these are more or less physical treatments. So allow me to share my screen and we'll discuss all these things. So this is unit week 5 and we'll be solving some sample problems and I'll share the polls so you can see and answer in the polls. Polls option are present in the right bottom corner of your screen. I'll keep on admitting students. So meanwhile you can solve these things. Let's see this question number 1. This is question number 1 and these are the polls for question number 1. You can answer this question. Sedimentation as well as settling is an example of unit processes and unit operations. As sir has explained also I have explained it again, unit operations and unit processes are basically depending upon if the process is physical or chemical. So you can try to answer this question in the polls. Sedimentation or settling. This is the tank in which water as well as some organic and inorganic compounds are present. So this is the initial height of the water and compounds. After some time, what will happen? These organic compounds will settle down. Okay, so this process is referred to as sedimentation or settling. So what is this? Sedimentation is unit process or unit operations. You can answer the question in the poll section. Okay, we'll see the solution now. So answer is unit operation. As I have already told you that yeah, thank you. But the answer is unit operations. Unit processes are chemical in nature. What we do in unit process, we add some chemical that will help us to separate the contaminants from the water. And in unit operation is purely physical. As in this case, gravity was working. We are not adding any chemical, we are just allowing it to settle under gravity. That is why this is unit operation, not unit process. And reference from where I found this question is here. You can refer this slide and you can understand the concept. In case of any doubt, you can ask me also. Moving towards next question. Question number 2 is grid chambers are located before bar screen, after equalization tank, after sedimentation tank, or after bar screen and before primary sedimentation tank? This is what you need to answer. Grit chambers are basically used for inorganic compounds. So where do we place them? Try to recall from the lecture. The placement of all the units is very important. If we are placing it properly, we will get very good quality of water. If we are not placing it properly, we just cost will be wasted, just money will be wasted, we won't get anything effective. So this thing is very important. Okay, we will see the answer. Answer is after bar screen and before primary sedimentation tank. What happens? We know, we have seen our nalas and all, and we have seen that there are lots of water as well as there are big particles. So first of all, what we will do, we will separate these big particles from our water. Big particles means papers, paper, chips packet, any food packet, as well as fallen leaves, trees. So first of all, we will separate these. So these are bar screens from which water is passed and these big particles are separated. Then comes the grit chamber, the thing which we are talking about, grit chamber. Here, the inorganic particles means sand, silt, all those things which will not degrade, okay, which will not produce any smell, those things are settled. Water will pass and these things will be settled here. Then after we will go to the sedimentation tank. Sedimentation tank problem we have discussed in question number 1. Here things will settle down again. Okay, but here few organic things will be settled down. This is sedimentation tank. Organic things will be settled down. Here inorganic things. We don't allow organic things to settle. Okay, so where are the grit chambers placed? After bar screen and before primary sedimentation tank. So this is the sequence. This is the conventional sequence you need to remember. Moving towards next question. This is question number 3 related to the same. The detention period of grit chambers is of the detention period of grit chambers is of the order of, as I have explained in the previous question, that first of all we put bar screens. I'll first launch the poll for this question so that you can answer in between. First of all, we have bar screen to separate out big particles. Then we have grit chamber. Then we have our primary sedimentation tank. Then we have other things. We have conventionally biological treatment, secondary treatment. Okay. So you need to tell what is the detention time in grit chamber. Detention time means for how much time water stays inside this chamber. Means if a water particle is here, entering here, how much time it will take to transfer from this side to this side. This is what we call detention period. How much time it's gonna take. This you need to answer. And remember, we don't allow organic particle to sit. These are organic particles. We will allow only inorganic particles to sit. Okay, so timing will be very less timing. If we will provide more timing, these organic particle will also settle. We don't want that. Okay, we want only inorganic particles to settle. So timing is very less. So what can be the timing? We'll see the solution. So timing is 1 minute. In 1 minute, however the big detention chamber is, we will the particle will move from this location to this location in just 1 minute. And these inorganic particles are heavy than the organic particles, so they can settle in 1 minute, but in 1 minute these smaller particles won't settle. So that is what we want. In some grid chambers, timing is 30 seconds also. So it should be less than or equal to 1 minute, not more than that. Moving towards next question, question number 4. The equalization tank is used to eliminate variations in flow, improve performance of downstream process, balance fluctuating concentrations, or all of the above. And these are the polls for question number, uh, I think these are the polls for question number 4. So why do we use equalization tank? Where do we put equalization tank? We can put equalization tank here as well as here, anywhere we want. So what is the use of equalization tank? This tank itself does not provide any treatment. Okay, it just holds the flow for a while. So why do we use it? Let's see the answer. So answer is all of the above. Here you can find the difference. So what does equalization tank do? Just example, in one day you are getting 5 mld of flow, and some days you are getting 20 mld. So you have designed this tank for 20 mld flow, but you are getting 5 mld someday. So the further process electricity is used, same amount of electricity as well as manpower will be used to treat small flow, but we can treat more flow also. So what this tank will do? This tank will keep on accumulating the flow until the maximum flow is reached. Then it can go towards further process. Second, this is first point. Second point is what happens in the downstream processes. If we will put for 1 minute 5 mld, another minute 10 mld, so what happens? The further processes won't be able to survive, especially the secondary processes. In secondary processes, we use bacteria, we use algae to treat our water, wastewater. What happens if you will put, uh, just imagine some acidic waste is coming, we will put 4 pH 4 acid, sometimes pH 6 acid. So the bacteria will die, no? That is why we use equalization tank, so that the quality as well as quantity of the water can be stabilized. Then we transfer that to further process. Okay, so all of the above is the answer. We'll move towards next question. Removal of suspended organics and finer inorganics usually takes place in suspended organics and finer inorganics. Inorganics I have told you in grid chamber. Okay, but where there suspended organics also takes place, where the settling of suspended organics also takes place, and finer inorganics, so they'll be there only. Okay, we'll see the results. So, answer is option C. In grid chamber, as I have told you, we allow only organics, only inorganics particle. We don't allow organics. Next, when we talk about primary sedimentation tank, these inorganics are settled. So there will be some small inorganic particles that we will be settled in primary sedimentation tank, and some organics particle will also settle. So answer will be primary clarifier or primary sedimentation tank or PST. We'll move towards next question. Question number 6. The critical settling speed, or we generally refer as velocity, is equal to overflow rate, settling velocity at which all the particles are removed irrespective of their size, maximum settling velocity of particle. So what is critical settling velocity? You can try to answer this question in the polls, then I'll explain. Okay, we'll see the solution. Solution is A equal to overflow rate. This is the critical settling velocity. Okay, so overflow rate is at what rate we apply wastewater in any system. At what rate we are applying water is what we call overflow rate or critical settling velocity. If the particle settling velocity is more than overflow rate, it will settle. If the particle settling velocity is less than overflow rate, it will not completely settle. It will not completely remove. It will be removed in some reference. This is particle settling velocity and this is our overflow rate. Okay. So if settling velocity is more than overflow rate, all the particles will settle. If it is less than, then it will be settled in ratio. We'll see. Next question. Surface loading for a rectangular sedimentation tank with length L, width B and height h having design discharge of Q is represented by, surface loading means velocity we want to find out. You can find out the velocity that will be represented by this problem. I'll share the polls. You can answer this question. We'll see the result. First of all, I'll draw this thing. Just imagine this is a sedimentation tank. This will be the length. This is the width and this is the height. Some wastewater flow is coming. It's coming, just imagine from the top. No, it won't come from the top, it will come from the side. Something is wrong with my pen. Wastewater is flow is coming from the side. So the question is, what will be the surface loading rate? We need to answer this question. So what happens? Surface loading rate, what we want, our target is to settle the organics. Organics will be settled, and we want to settle what happens in PST, small or inorganic particles as well as organic particles. We want them to settle with the velocity of V naught, means surface loading rate. So surface loading rate will be this whole, how much water is coming, Q is coming, direction of velocity in the downward direction. So what dimension we will use? This thing and this thing. We just want this because velocity direction is downward, so we will take only these two dimensions. So we will take B and L. In case of settling velocity, we do not take care of the depth. Depth is not an important factor in this case. So your answer is B Q upon BL, and you can refer here for that. Coming towards next question is question number 8, and I'll launch polls for it. You can answer this question here. The overflow rate of sedimentation tank is, it is also called surface loading. It is independent of the depth of the tank. We have just seen this thing, or this thing also. Depends upon the length and width of the tank. Just seen this thing. So you can answer this question. This is very easy question. You can answer this. We have just seen all the aspect of this question in the last question itself. Okay, we won't spend much time in this question. So answer is D. What we have seen, overflow rate or the surface loading rate is equal to Q upon BL. So there is no depth. It is independent of depth. Depends upon length and width. Yeah, it's depending upon length and width. So this question is done. We'll move towards next question. That is question number 9. Select settling velocity is typically highest under. This is what you need to answer. I'll show the polls for this one. Discrete settling, or we call it type 1, flocculent, zone settling or compression settling. In discrete settling, particles are separate. They do not interfere. In flocculent, particles are in flocculent stage. They are little bit combined. In zone settling, particles affect each other. One particle will settle, it will take care of other particle as well. All things will be settled at zone. This is one zone, this is second zone, third zone, like this they will settle. In compression settling, the particles are concentration is so high that the above particle will settle down the downward particle as well. So this happens when the concentration is so high. So settling velocity will be highest in which case? We'll see the solution. So the solution is B, flocculant settling. Why? Why this will be highest? In discrete settling, we will take as reference. In discrete settling, particles are settling. In flocculant settling, since many particles are combined, so their specific gravity will be increased. So sometimes the speed of flocculant will be higher than discrete. Okay. And in zone and compression settling, what happens? They are settling. They are in cluster. They are settling, but they will get equal resistance from the from the water particles present. That is why the velocity decreases. So that is why the flocculant settling velocity is highest. When you will do experiments, you will find this thing very easily. So this is question number 10. I'll launch polls for it. Which of the following is tertiary or advanced treatment process in wastewater treatment? So typically, what treatment we do? We just do primary treatment and secondary treatment. Tertiary treatment we do if we want to put water in some special use. That is why we do tertiary treatment. Either we want to reuse it as drinking water, or we want to recharge groundwater. So if there is any specific purpose, we do tertiary treatment. So in what we do in tertiary treatment? Do we remove heavy metals or high TDS or high nutrients? What do we do? This is very easy question. How? Just imagine what kind of water you want to drink. You want very high nutrients, or you want very high total dissolved solids, or heavy metals. So this is what we do in tertiary treatment. You can answer this question. We'll see the answer. So answer is D. All of the things we want. We will remove heavy metals. There are various heavy metals like mercury, chromium that may cause even death, even in very small amount. In mercury poisoning, there are lots of effect. We will see graying of nails. Nails will become gray and brittle. Arsenic, it will cause many skin diseases. Fluoride, this may also cause many problems. So we want to remove these metals. Fluoride is non-metal, but arsenic is metalloid, so we consider it as heavy metal itself. Removal of high TDS. If there are lots of TDS in our water, so that is very dangerous for us. For example, fluoride is there, so it will make our bones brittle. Okay, that is why we want to remove these total dissolved solids. Nutrient. Why we want to remove nutrients? Our body requires nutrient, but in very small quantity. Okay, there is one nutrient, nitrate, that is nutrient. So what happens if for a baby they will get, if lots of water with this nutrient goes inside their body will turn blue, they will die. So that is why we don't want nutrients, this amount of nutrients in our body. Okay, so moving towards next question. Question number 11. The tube and plate settlers compared with conventional sedimentation tank generally requires. So this is our sedimentation tank. We will use plate settlers like this. This is the whole height. We will put tube settlers. Sometimes we put them straight, sometimes in some angle, just to increase the surface area. So what all the things from this list we need? One of them is correct. I'll launch the polls for it. Lesser area, higher input energy, lower maintenance, or more area. Like it's all about if we want more area, or if we want more input energy, or higher maintenance. What do we think tube and plate settlers will do to our conventional sedimentation tank? We'll see the solution. The solution is D. They require less area, lower input energy, and higher maintenance. See, what happens? Our conventional treatment sedimentation tank is treating this area, this big area, means bean to L. Okay, when we will use plate settlers, and it is treating like, just imagine it's treating, treatment efficiency is 95%. Okay, when we use plate settlers, for the same treatment efficiency, area required will be very less. Okay, area required will be less than bean 12. So lesser area is there, lower input energy. Because the area required is less, so less motor, like we use pump to pump water into the sedimentation tank, right? So less power of pump will be required to fill this. That is second thing. Now, but higher maintenance are required. In conventional sedimentation tank, we can use one scraping mechanism and clean this bottom and walls. But if tube settlers are there, like this, we need to clear everything. This, then this. So maintenance cost increases. That is why higher maintenance are required, and that is why these are not like used everywhere. This is question number 12. This is numerical type question. You can use calculators to answer this question, and I'll launch poll for it. Determine the approximate detention time of grid chamber with the settling velocity. Settling velocity is 0.02 meter per second. Depth is depth is to width. Depth is to width is equal to 1.5 is to 1. For treating maximum wastewater flow, Q we know 1000 meter cube per day. Flow through velocity means velocity of flow is 0.3 meter per second. So we'll see this it like this. Just imagine this is a grid chamber. How much flow is coming? 1000 meter cube per day. Flow velocity is 0.3 meter per second. Settling velocity is 0.02 meter per second. And height is to width is
Ma'am, wastewater flow is 10,000 meter cube per day.
10,000 meter cube. Thank you. Okay. 10,000 meter cube per day. Velocity of flow is this much. Settling velocity is 0.02 meter per second. And we know the ratio of height and width. So we know this side. We know something about this side. This is height and this is width. Okay. So what we will do? As we know, Q is equal to area into velocity. Okay. So area is equal to Q upon velocity. This is very important. This is called continuity equation. We should remember, this is true in every case. So q into velocity. So we will find out this area. Okay. How to find out? Q into velocity, q divided by velocity, 10,000, and velocity is 0.3. We will get the area, and area is equal to width into length, width into height, and height is 1.5 times of width. H by B is equal to 1.5 is to 1. So height is equal to 1.5 times of width. We will put it here. So 10,000 divided by 0.3 is equal to 1.5 b square into b square. Okay. How much is b? We'll use calculator to solve this question. I got my b as 149.07 meter. Now we know b. Okay. And we need to find out the detention time. Detention time is either length divided by retention time is how much time a particle will take to travel from here to here. Length divided by flow velocity or volume upon q. In every case we need, see, we have b, we have h we can find out 1.5 into 149. So we, for volume we need L, as well as for this equation we need L. How to find out L? We have this velocity. We can find out this area. This area we can find out how? We have Q, A is equal to Q by V, right? We have Q 10,000. We have this velocity 0.02. What will be answer? 10,000 divided by 0.02. We got 50,000. This area is 50,000. And what this area is composed of? Length into width. B we know. So L is equal to 50,000 divided by 149.07. Answer is 3. Oh, we are making one mistake. Very big mistake. See, Q was in 10,000 meter cube per day and velocity is in meter cube per second. So first of all we need to convert this to meter cube per second, right? So 10,000 divided by 24 divided by 3600, we will get 0.1157 meter cube per second. So these things will change. This is 0.1157. So B we will get as 0.5 meter, 507 meter, and here it will also change. Here area will be 5.785 meter square. So L what we will get? Divided by B. L is 11.41 meters. I hope you are understanding what I am trying to do. I will give this recorded lecture as well as the solution, the clear solution. If there is any doubt, you can ask me in the next session. So, what will be the time? 11.41 meter upon flow through velocity, because particle is moving from here to here. Flow through velocity is 0.3 meter per second. 11.41 divided by 0.3 is 38 seconds, which is matching to the first one. I'll clear the slides, then I'll show you the solution. This is the solution. Here they have solved it very short, so you can understand the question. The timing is 38 seconds. Moving towards next question. For problem number 12, determine the length of the grid chamber. We have already found the length of grid chamber, that is 11.4 meters. Okay, 11.4 meter was the answer, right? Yeah. So we'll move towards question number 14 now. I hope you are getting how we are finding this thing. So there is some different approach. This approach is quite different that I have followed. So you can refer any of them. I'll give you lectures as well as these slides. So this is question number 14. The terminal settling velocity of this particle. What is the particle size? 0.01 mm. Specific gravity 2.65. Density of water 998.2 kg per meter cube. Kinematic viscosity 1.002 into 10 raised to power minus 3 Newton second per meter square. There is one thing, kinematic viscosity and dynamic viscosity. So dynamic viscosity is equal to kinematic viscosity divided by the density. So 1.002 into 10 raised to power minus 3 divided by density of water 998.2. What we will get? 1.002 into 10 raised to power minus 3 divided by 998.2. We are getting 1.004 into 10 raised to power minus 6. This is what we are getting, kinematic viscosity. What is the equation of velocity? This equation is called Stokes equation. It is g by 18 gs minus 1 dp square upon nu. This is kinematic viscosity. What we will get? 9.81 value of g by 18 gs minus 1 2.65 minus 1 dp square. Units will be should be the same, so 10 raised to power minus 3. To convert this millimeter into meter, square divided by 1.004 into 10 raised to power minus 6. When we will solve this, we will get the answer of velocity. Then what we will do? We will this is Stokes equation, right? And Stokes equation is only valid when the flow is laminar. And what is laminar flow? Laminar flow means Reynolds number should be less than 1. And Reynolds number is velocity into diameter divided by kinematic viscosity. Look at this difference, kinematic viscosity and dynamic viscosity. So kinetic viscosity, this should be less than 1, then only this equation is valid. So first of all, we will find out the velocity, then we will check if it is coming less than 1. If it's less than 1, then only we can say okay, this velocity is correct. If it's not coming less than 1, we will use a different equation for velocity. So we'll see the solution. I'll clear it, then we can see. I hope these things are small, but I hope they are visible. So first of all, we are assuming laminar flow. So, and we are finding the velocity by Stokes velocity. What we got? Velocity is this one. Then we checked if it is laminar or not. When we find out this was less than 1. So therefore terminal velocity calculated is correct. Means the flow is laminar because Reynolds number is less than 1. So this is the correct answer. If it's more than 1, then we will use different equations for finding out velocity. Moving towards next question. What is the head loss through a bar rack with an approach velocity of 0.6 meter per second and velocity through the screen is 0.94 meter per second? How do we calculate head loss? I think it's 0.0729 b square upon v a square. Approach velocity is a. So 0.0729 0.94 square minus 0.6 square. Whatever we'll get, it will be the head loss. So the solution is 38 mm. This is the correct answer. This is how we find out the head loss. Head loss, what head loss means? If this is bar screen, the level of water is flowing through it like this. And this is the horizontal thing. Here height is h1, here height is h2. So head loss is difference between h1 and h2. So this we can calculate from this equation. Okay. If the head loss is more than permissible, what we can allow, we will clean this screen. It means this screen is very dirty. So moving towards last question, this is the last question, then we will close. The settling basin at a wastewater treatment plant having the flow rate of 0.6 meter cube per second, Q is 0.6 meter cube per second, has an effective settling volume, that is we know the volume is 20 into 3 into 6. What percent of particle that have settling velocity of this will be removed? So first of all, we need to find the settling velocity. Okay, settling velocity we know, we need to find out overflow velocity. What was the formula? Q upon BL. Depth will not be considered. So that will be 0.6, L is 20 and B is 6. From this we will find out V naught. What is V naught? V naught comes out to be 0.005 meter per second. So what percentage will be removed? This is the solution, 60%. How? This percentage efficiency is equal to settling velocity upon overflow velocity. 0.003 divided by 0.005, which comes out to be 0.6 in percentage at 60%. Okay. So this is how we solve this problem. If this settling velocity is more than overflow velocity, means all the particles will be removed. So this is the end of this today's lecture. I'll stop sharing. So any doubt? If in case of any doubt, you can ask, or you can ask in between also. You can mail me, as well as you can post the question on the question answer forum of NPTEL. So we'll stop the session now and see you all next week. Thank you. Bye bye.